So my name is Julian Thomas, and I'm happy to be here at Besides Budapest after being an activity. So we'll talk on the subject called in-app virtualization to bypass Android security mechanism on not rooted devices. So this study is part of the Protektoid project that we are working on now for quite a couple of years. So it's quite a long talk that I will try to make short because I have a lot of things to talk about. So I will quickly have an introduction about what's about, then mention two core principles, which is what we call patching and what we call proxifying on Android, but like also the general term, and then a real consideration about how can that work in real life, because it's good to have theoretical point of view, but also like how can we make that work together to have something that really works on real devices. And then, and after much kind of a review about that, what we can how we can deal with that, and a conclusion. So the objective of this talk, as I said, is to talk about patching and proxifying and the limitation of Android security caused by that. And what's important when talk about security is good to have good security, but it's also good to show that in a good way, so that we cannot play with limitation of user knowledge and user perception to trick them. Even if the system is secure, it should not be possible to do it. But if you can do it in a way that users don't understand, well, they will agree, and then you will be able to do what you want. So that was the first thing. And the second thing is that we will have another perspective, because here again, when we talk about patching of memory in Android, well, most of the time you consider like you have root access, you proxify libs into processes. Well, it's good to also be on the other side, which means like you're only an app. You're an attacker, an app, so you have basically no capability on the system. You don't want to be detected, because if you're detected, then you get removed. And well, what you can do when you're under such circumstances? So as I said, this is part of the Protektoid project. And what I always like to mention when I have a talk is like, where does that come from? So in activity, I said that it's come from an ability to decide about the application that try to connect to internet that we started the whole project. Well, now it's like we had another issue, which is how does application hide other applications? I mean, there's quite a lot of applications pretend or do that, but how does it work? Because it's normally not that possible. So before talking about like memory, writing, patching, and proxifying, I was just curious about two general questions for the audience. It's like, who knows about memory patching method, address patching on Android? Nobody heard about that? Okay. So I'll try to explain that. And the second question, because I'm talking about the second subject too, which is proxification, or what we call in-app virtualization. So virtualization on Android, like plugins on Android, does that ring a bell to someone? Okay. So when I say memory writing, we have to consider three types of code. So we have the native code, because on Android we can have native libraries inside application, so it's executed. Then you have the code that is pre-compiled or compiled depending on the version of Android you are working on, so what we call JIT, or ahead-of-time compilation. Then at some point, other part of Java code is sometimes compiled or not. Okay? And all of this execution flow is set in memory through what we call ART structure. ART stands for Android Runtime. So when we talk about Java methods, mainly the virtual one, which is kind of the public methods, well, what we can do about them is that if we're an application, we can self-patch. I mean, like we can rewrite your own memory, we can override DEX, and we can also play with what we call, and what I will explain through virtualization, sub-loaded applications. We can play with the memory of applications that we launch within our own context. And obviously, all of that is done at the C level, so through GNE bridges, to be able to control that on Java level. So if we look very quickly about the workflow, so that's a little redesign, but that's the Android documentation. What we have here is that we have the code that is ART mapped, and then it's executed. So depending on the version, we have on Android either it's AOT or a GIT, and if it's none of them, then we try to we try to run it, to interpret it, and if we can compile, well, we will compile it. So basically, we do quite a lot of things. But what's interesting is that here, basically, we try to put some things in memory, sorry, and that's where we can play. So before explaining everything, I mean, I will try to do the demo if I can show it, because it's still interesting, I believe, is that, let's say we have this environment. So we have an application that do 4 types of connection, one which is pure HTTP, one that does HTTPS, like raw HTTPS without any security consideration, we just do HTTPS connection. Then which is HTTPS connection with a custom trusted manager, so like we'll restrict the set of certificates that we consider as being trusted. And the last one, which is like we do HTTPS connection with a sub-restricted set of trustworthy certificates and a custom libraries to do the HTTP. And obviously, as I said, your device is not rooted. This hub that I mentioned is safe, like it doesn't have a bad behavior in itself. And you install what I would say a nice, I mean it's not that nice, but it's nice, launcher application that you call launcher. So we have a lot of instances on the Play Store. I mean it's not like a random idea. Like you have desktop launcher, you have privacy vaults that do exactly that as a purpose, like they launch other application. And the question is that, okay, what can be done? I mean, like, in theory, nothing. Like, I mean, like, we cannot break the HTTPS process. Well, in fact, that's not really true. I mean, like, obviously, you can easily monitor HTTP connection. I mean, it's HTTP. You can, like, destroy the default implementation of HTTPS to spy on HTTPS traffic of this application. What you can also do is by combining both virtualization and patching, where you can also unset the trusted manager settings on Android, and basically you will say that, no, trust my certificate even if it's not a good one. The last one, which we are still not able to do, but we're working on, is to bypass custom HTTP libraries. So if these custom HTTP libraries rely on underlying, I mean, on Android and on Java, well, that's easy to do. But like if it's really standalone library, and I will explain why, we're still not able to bypass the security. So I wanted to show a demo. I will try to load that from the web and hope it works. I mean, normally I have that on my key, but not is working here. So like basically here we have an application that does this full connection type, pure HTTP, pure HTTPS, HTTPS with trusted manager, and custom HTTPS through, if I remember correctly, it's OK HTTP library, so it's not system loaded. Okay. So if we do the connection, like default connection, everything works as normal, like nothing is proxified. Okay. So like we will relaunch this application and try to proxify the HTTP and HTTPS connection so that we monitor them. Obviously, by default, well, there is no way it should work. I mean, like we cannot have a man-in-the-middle proxy with like a custom HTTPS certificate that try to listen on you. I mean, like that's not possible. So I will have to say on that one, trust me, because I don't want to waste. But basically, that does not work. I mean, like it's kind of pointless to show something that does not work. Like I mean, like you cannot spy on HTTPS traffic. And if that loads, okay. So anyway, I will make the demo available. So if you want to look at that one later. Anyway, the explanation will show that why and how it works. Okay, so sorry for that, but basically the idea is that you can build a proxy, so it can be local, it can be on the web, wherever you want, and you can spy on HTTPS traffic that is either relying on default Android Java settings or with the Android Trusted Manager restriction. So sorry for the demo, I will make it available. So core principle of patching. So, as I said, very important distinction before and after ahead of time compilation. So, like basically before and since KitKat or since Lollipop. So, what we had before is that we have the Dalvik, which is kind of the JVM for Android, so Java Virtual Machine, with what we say, sorry, just-in-time compilation. So, it's not pre-compiled. Then we have, since that, ART, so with ahead of time. So basically, when you install an app on a device, it's pre-compiled to improve performances. However, even if that's just an implementation distinction, the underlying structure remains the same. Okay. So if we look quickly at Dalvik structure, so we have here what we call the class object. So what's important on this class object? We have a lot of data here. It's not really important. Then we have the method. So here, for example, we have the pointer to the table of virtual methods and the pointer to what we call the virtual table that is used to basically jump to the address of the method. And here on the method, we have what we call the method index and the class. So basically, when you call a method, it will look for the class, it will look for the index, and it will jump at the correct index of what we call the v table to get the address of the method to launch. So if you want to patch that, it's kind of very easy because like I put here a mention of a blog post where you have everything very well described, like it's nearly like there. I mean, like you just have to use library that is available to patch it. You just have to be careful about how you do that, but basically you just have to say find class, find new class, find old class, then jump to the, then get the new method address, and then put this new method address inside the class that you want to patch correct vtable entry. If we look at since Lollipop, so not Dalvik, but like precompiled, well, we can say that, oh, well, it's very interesting. We have the same thing, vtable, virtual methods, method index. And like it's really similar. I mean, as I say, it's quite normal because the logic is the same. What we try to improve with, what they try to improve with this ahead of time compilation is not reviewing the logic, but it's improving the performances. So the logic is the same. So obviously, the Dalvik virtual machine is not there anymore for just-in-time compilation, so we cannot use on the previous mentioned method. However, we have new method now available, which in fact do nearly the same thing. So you just have to switch the code, but the implementation, the underlying patching logic is again the same. So which is very interesting because it's kind of easy to make a multi-Android version compatible patching framework. So that's what I try here to summarize that basically if we just abstract the exact implementation where we have a class, a method, we look for the class, then we go to the, what we call here the vtable to just get the new address, and then that's how the execution flow normal one works. Well, if you want to just patch it, we just have to basically just overwrite here the pointer to say, no, the pointer is here. Then you have to do the correct implementation depending on the Android version, but the logic is here. You just have to like basically change two pointers in the memory to be able to patch. A little distinction is that, as I will show later, it's not that easy because basically when with IRT and Android, so since Lollipop, like when to move to new version of Android, they have this nice idea to also move the implementation of the ART structures. One of the examples is to move to 64 bytes instead of 32. Well, obviously that impacts us in the way where are the index and the structure we want to modify. So what's the patching objective? I mean, like, what do we want to patch like that? I mean, like, what we want to patch for memory? I mean, like, it's not a lot of things. Well, you can just change very few stuff. You can change the execution flow. So basically, if you want to have someone that type on the text, well, it can be also automatically copied to the clipboard for easy saving wherever else. So it's nice, but like the real usage are limited, except maybe if you want to misbehave the user perception, but it's not that much. And the source code I mentioned above and the link I put, like we have already quite a good set of libraries that does that. Whether it's invasive or non-invasive approach, you can already patch quite easily with these libraries the memory of Android. Okay? But the issue is that here it's basically viewed as a security tool point of view because nearly all of the time you need to have a rooted device or even need to have new frameworks or exposed or whatever framework. So that's not what we want to do. We want to do like, we don't want to be rooted. We want to be like a basic application, so that's not good for us. And here come the second aspect of this presentation, which is what we call in-app virtualization or proxifying. I don't want to play on the game, so I mentioned both. So if we have dynamic code loading, so what we say is that we can basically put a DEX file, so like a separate DEX file, on an application and put that in memory after the application launch. So that's why we call dynamic code loading, so you can, I don't know, dynamically load Java methods and execution. So it's used most of the time by malwares. I will not say most of the time, some of the time. And it's also used to dynamically load code. So like we have multiple purposes to do dynamic code loading. Like if you want to patch an existing application without following the update mechanism of Android, I mean, like normally it's not permitted, but you can do that. If you want to launch frameworks that is user specific, so you have not always bad intention with dynamic code loading, and that's maybe the problem. Otherwise, it would have been easy, like you just like block dynamic code loading and promise solved. But no, because this is used by a lot of genuine applications, so you cannot do that. And I think that you can also look at two very interesting studies, which is like one of the Symantec reports, which is that in fact most of the time the implementation of dynamic code loading misunderstands how it works on Android and like is subject to a lot of vulnerabilities. So if your applications that do that, well, just do not trust them that much. So here it's good, we can load code, but it's not mean virtualizing application. I mean, like that's a step above if you want to really virtualize application. When you want to virtualize application, what you want to do is like you want to start a new application that the user sees that as a new application, not as a feature, not as a button click. No, no. What you want is that these applications that behave like it was normally launched. So basically what you want to do is to launch the application, to do thread attachment, to launch threads, and to preserve all the Android workflow that comes with the execution of an application. So when you launch the application, it's create a new process, then it threads that, then if you have services, it's new services, it's new processes, sorry, for the services, you have user ID. And well, you have libraries that deal with all of that. And it's very cool libraries. So before mentioning that, I just wanted to mention some terminology about Proxify versus Proxy because I use that as shortcut later on. So the Proxify is kind of the host app that is doing the proxification, and the Proxified is the hosted app that is being proxified by the proxifier. And we have here maybe two important concepts, which is virtual activity and the virtual service, which in fact are activities, so normal activities, but launched under the control of the proxifier, and the same thing for the services. Okay, so what's the objective of virtualization? Because here again, if it would have been obvious that the intent was malicious, well, it would have been blocked or somehow discredited. Well, you have a lot of applications that do proxifying for, let's say, genuine reason. One is that you want to vault apps and hide them from the system or from other users. Basically, when you launch the Android, if you vault apps within these proxifiers, nobody sees them. Nobody can run them if the vault is password protected. You can also what we call multi-instantiation approach. So that's maybe one of the main objectives, both privacy and multi-instantiation. If you have an app that does not support multi-instantiation, I think Twitter does that now, but before it does implement multi-account, well, you just have to multiple time virtualize Twitter within this proxifier to be able to have multiple instances of Twitter within your own Android. I mean, like, it's not a joke, like, people do that. I mean, one interesting stuff is that, well, when you start to do that, you know that you are totally outside of standard execution scopes, meaning like updates, not managed. Security of the execution of this application, I mean, nearly virtually zero. So I think that's quite interesting that by simply proxifying, you can do all of that. You have all these disadvantages, and nobody really understands that because of user misperception. Okay. So how proxifying works? I mean, I put some gray here. I mean, it's very easy to know which library I'm mentioning. But I don't want to be the one that discloses these names, so I prefer not to. So basically, what you do is that, well, you just have to handle here, as one I'm trying to mention, is that here what you do is that you init a new process through what we call a virtual activity manager, because normally you cannot do that. I mean, like, there is no way you can launch a process on Android that is an application. That's normally that's the goal of the Android system and the forgot the name of this daemon that handled that. But anyway, so it's not possible. So we virtualize the execution of a new process. And you virtualize the launch of this application. All of that happens under the control of the proxifier. Okay, and to be able to do that, what you describe in your manifest of the proxifier is that you describe new activities here that have this very specific process attribute that says, no, when you put this activity that is dynamically loaded, don't put that in my process. Put that in a new process. And basically, we have the main activity of a new application that is launched in a new process, which is what we want to preserve normal execution. And if we look here at the process status, what we see is that here I made this the networking application, which is the application I wanted to show in the demo, that is virtualized, and you will see that they share here the same user ID as the proxifier. I mean, they have new process ID, which is what we want, but they have the same user ID, which means that they are being proxified. Okay. So how proxifying works? Step 3. So you virtualize user ID of the application. So even you can have multiple user enabled to have multiple user ID based on the application ID. So you do whatever you want, basically. And real estate is preserved, as I said, because when you do system calls, like if you have the ID 10003, for example, for the third application that is being virtualized, well, you cannot say that to the system because it does not exist as a user ID, or it's even a system ID. So you have to say, no, when you want to do a system call, just use the proxifier user ID, which is the one that the system sees and knows. Okay, so virtualization explained, patching explained. Well, how does that work together? So why doing both together? Why simply not doing proxifying? Because there's quite a lot of good feature ready for us. So if we do not do patching, we'll just proxify and see what we can do from that. So first, a feature that is very interesting is that the normal execution is preserved. So basically, you don't have detectable payload. Like it's not a payload that is added to the proxifier. Like you can just take an application that is on the system, proxify it out of the box, and run it, and well, it's here, proxified, no code loaded from anywhere on the web. It's just like loaded from the system itself on another folder because it's available for everyone. And you can also have what we call Byzantine approach, meaning like if you want to not be detected, you just can trigger the virtualization on demand. And you can also do is trigger user-specific decision, meaning here again, when you have a virus, it's easy to spot that it's a virus because I've been doing a lot of malicious activities on a lot of other applications. When if you have a Byzantine approach and a user-specific approach, it starts to be more difficult to spot them. So if you do that still only proxification, you have a lot of things to do on the proxifier side. You have to implement two main things, which you have to implement what I call the set of permission from all the hosted apps, because the system sees the proxifier, not the proxified. So if a proxified application wants to access contact, if the proxifier do not have access to contact, it will not work. So you have two approaches. Most of the time, what the proxifier do is that they request everything that proxified apps could have. It's easy to spot them. So you can say is that, oh, you just implement, for example, contact access because that's what you want, and you deny any other permission as requested by the proxified because you control them. And you have to do another thing, which is bridging file system for hosted apps, Because on Android, each app has its own private directory that is controlled by normal Linux permissions. So you just have to bridge this private directory to the private directory of the proxifier. If you do that, well, an app will work and run, a proxified app will run nearly out of the box, and you control the file system. So what you do here is that, as I said, you bridge the file system on the private directory of the proxifier. So basically use the user ID of the proxifier. So you see, control, can delete, can read all the private data of the proxified apps. Another thing that is fun is that, well, you can also preset the default environment settings. So as I said before, you can, for example, bypass the HTTPS default configuration on Android, and you can bypass also the proxy, default configuration to say that before or after I launch this new activity in our own process, we'll just preset the HTTP proxy environment on Java side, so system. Just preset the default trusted certificate manager. So basically you can say, oh, redirect to, I don't know, I will not mention country, so to IP 1111 and trusted certificate trust everything on the world. And basically all your traffic, may it be HTTPS, will be redirected to the man in the middle proxy 111. And as we trust any certificate, even invalid one, well, it will work. So that's what here I mentioned, is that here if you just put here this set property on the system, so the proxy host and the proxy port, well, you redirect all the traffic of these hosted apps to the specific address by default, like you have nothing to do. And here if you preset the HTTPS configuration to the set default SSL socket factory of the hosted process, well, you say basically here that, yeah, is it a valid host name? Yes, true. And here, do I trust the certificate? Yes, trust everything. Well, you can access all of that. Okay. So patching from scratch. There's a question. Can we patch from scratch? Yeah, we can patch from scratch. I mean, I tried to patch from scratch. That was fun. I think it's important to patch from scratch and not use libraries, because that's where you understand the distinction between Dalvik and ART. You understand the distinction between each version of ART, and you understand what you can and cannot do. Because if you use libraries, you will be very quickly limited about the understanding of what you can do. There are a lot of work on Dalvik. Far less, surprisingly, on ART, even if I would believe that it's far easier to do. And yeah, the mention, I think, like when you do Java for a long time, you're quite pissed off not being able to patch memory. So I think it was very funny to patch from scratch to be able to GNI bridge, memory patching. I mean, like, that was just for myself quite fun. So okay, easy, but in fact not that easy. Easy to waste a lot of hours. Yes, that's super easy to waste hours because of incorrect documentation. It's easy to waste hours because, well, if you do not pay attention that this map from 32 bytes to 64 bytes on the new version of Android, well, surprisingly, you jump in the middle of addresses, which is kind of doing segfault and not good. And what you need to know also is, in fact, what do you want to patch? What do you want to patch? What do you want to patch? I mean, like you have a lot of, the structure is not that easy. You want to patch the vtable memory, but you also have what we call the EF table. You also have the static methods. Can you patch static method? Can you not patch static method? Which DEX do you want to override? I mean, like you have the DEX from the system, and you have the DEX from the Proxify apps. I mean, like, what do you want really to do? So I will explain later what do you want to do, but like, I think that just patching from scratch is very good because like it raises all these kind of questions, then you understand better what you do. And as I said, patching from scratch is very complicated and boring because when you move from Lollipop to Marshmallow, well, you move to 64 unsigned instead of 32, but that's the structure and the pointer inside the structure are still unsigned in 32. So like it's kind of fun to think about that. So the question is like, yeah, I mean, is it really an option to proxy from scratch and not using simply libraries? Okay. Because if you see like this kind of codes, if you want to proxify from scratch, where you do this kind of methods, like if you don't understand why it's segfaulting, you start to print the memories, to look at the index. Yes, it's a good index. Yes, this index good because here I see that on the index 24 of the structure I have 4, which is the index of my method. So here that's checked, that's good. And here, yeah, if I jump at the end, yeah, I still see this 4. So yes, I'm patching the correct method. So that's what you have to look at. Then the second question is that proxifying correctly. Yeah, it's easy to proxify. As I said, just use a proxifying tool. But where, if you want to proxify and patch, where do you proxify? How do you proxify? When do you proxify? I see a lot of questions. And what we wanted to do first is to make a library that is capable of proxifying, within a correct application. And what we reach here is, I mean, that's the word description of the project, which is like you have a front-end launcher that is basically relying on the back-end for management, so that's an open source launcher. And when you can say that you can decide, do I want, yes or no, to virtualize this application? As I said, it can be on the user's discretion so that you are less easy detectable. Okay, so then you try to proxify it. If you do not succeed, you want to preserve, because sometimes the proxifying library fails. I mean, like, there are a lot of reasons for the failing, so you don't want the users to see that. So well, you just redirect to the normal execution flow, not proxify. And if you succeed to proxify, well, you start to patch. Okay, and if you fail to patch, you can decide what you want to do. Do you want to stop the proxification and restart the activity out on its own context or not? Okay. And if you do that, well, you start to have a quite very good silent patching project. So I mentioned proxifying only is already good. Like, you can do quite a lot of things: preset default settings, access local storage. What's the point of proxifying and patching? Because patching is not that straightforward. Well, you can obviously do everything as you can with proxifying if you do both. And you can also do something very fun, which is you can start to patch all the calls. So like, for example, if you want to check, do I have permission? Well, you just patch permission check. So you said, yes, permission granted. So basically, if you have custom permissions that are set on the hosted apps, you can just bypass all the checks through the patching. And you can lie about EPCs too, but I can mention that outside of this presentation. So the question is that, yeah, is that easy? We have the proxifying library, we have the patching library, we just put it together and it works. So, well, not really, because as I said, you first want to know where to patch. You know, like, for example, when you have a patching library, they do not do virtualization, so they have 2 decks, they play with 2 decks. Well, we don't want to do that, because as we virtualize, what we want to do is to play with the system decks. So what we will do is that the patching will just go on the system deck, look of the hooked, I mean, like, the main method you want to hook, we'll get the new method that you want to be the hooking point, and put that together, redirect them, and make it work on the proxified process. Which version of Android also is targeted is very important. Which method you want to use is important, because, for example, if you use a hard hook project which is in C, it works on KitKat and Lollipop, it doesn't work above. If you use Android, it's supposed to work on all, but you have an issue that is C++ code which fails to work with the proxifying library. So in fact, you end up with a very specific need, like if you want to be able to virtualize within a normal launcher, and also patch, where it starts to be complicated to rely on libraries because you start to have a lot of conflict between them. Okay? So here, the conclusion is that patching from scratch was very good because you can control whatever you want. So you just don't care about the proxification because it's too complicated to do on your own. You have too much things to do. Well, you can you can patch the proxifier, but you cannot really do proxifying from scratch, but you can do patching from scratch. Because even if that's complicated at the beginning, at the end you have a total control about the patching technique, which is really the most versatile part of the process, because you have to be Android version compliant, dependent, user decision specific, so that's where all the decision is very customized. So that's why here, maybe I was too fast. Yeah. So I don't know, like, if you can see that, but basically what you say is that you load the virtual method, then you try to say what kind of virtual method is that. If it's a virtual method where you patch it, it's nearly out of the scope, out of the scratch. If it's a static method, you can try to patch it, but if it's static native, it's not possible. So like, not all the methods are really easily patchable, or some of them are not even patchable at all. So you have to try and see if it fails or not, because sometimes even the vtable is empty, it's null pointer. So in that case, you cannot patch it, and you have to be very sensitive, because if you fail to deal with that correctly, well, the application crashes directly, like it's a SEC fault, a GNI exception, like that's total disaster because you get detected directly. So what happened at the end is that you have a very nice application that is being launched, being virtualized. This virtualization phase where it's normal execution. Then you start to patch. If you, at the end of the patching, you can decide either the patching is correct or not. If it's not correct, you can redirect to the normal execution so that users don't see it. Or even if you succeed to proxify and patch, well, you still keep that because that's very good. Then that's a win for you. So detection method, because that's not good. So can we detect that behavior? So you have basically 2 points of view to approach for that. One which is as a security app or as a system app, can you try to detect them? Okay? So can you try to detect malware by signature? Can you try malware by library signature? Well, here we are on the antivirus and the well-known complication to deal with the evolution of the malware side signature, so it's not really an option. Then within the app, can you do some things? Can you try to prevent an app from being virtualized? No, that was a topic presented at the Black Hat conference last year in Asia called plugin color, which they try to detect leaked data from the virtualization that can tell you that it has been virtualized. Okay, I will mention that later. Then what? I mean, like after you detect the virtualization, what do? You block the app. You ask for user consent. Like nobody really agreed on that, because if you ask user consent, do you want this application to virtualize? I mean, they will say yes, even if they don't understand what it means. Okay, how to avoid detection? Because as I said, I tried to get on the, not on the good side, but on the bad side, like we're trying to build a malware platform, so how can we prevent to be detected? First, if you're within the app, I mean, like what's cool is that the security feature is within the apps that you already virtualized. So, I mean, like the plugin is virtualized. So you can already first try to disable the plugin. If you fail to disable the plugin, can you try to prevent the detection? Because detection relies on virtualizable methods or virtualized method. And here, basically, you start to be kind of the virtualization game that, you know, when you have an hypervisor that try to analyze virus and another scope of various analysis, where you try to make virtualizer as stealth as possible so that the virus does not prevent its execution. Well, we are on the same side now, except that the hypervisor is a proxifier, so it's a virus. So if the virus succeeds to not leak any virtualization data, well, the application will not see it. You know, like for example, you try to hide how many activity you have, you try to hide the process ID, you try to hide the user ID, and basically the application will not know it's virtualized. Okay, what you can try to do is minimizing the virtualization library footprint. So by being only GNI bridge for most of the work, it's very hard to be detected. And as I said, you can try to minimize the virtualization feature by rebridging the app private folder. So that, for example, if you are a virtualized app and ask what is my folder, by default, you will say that your folder is /data /proxifier /0 /data /proxified, which is not really the one that you expect. So you will kill the application if you want to secure it. Well, you can lie about that. I mean, like as I said, you are on the proxifier side. So if you lie about that correctly, well, the application will believe that it's on /data /proxified, even if it's not. Okay, some issue we still have. Time loading is a very big issue when you do virtualization. Unless you're on a very good device, it slows down the execution flow. So we can try to solve that by preloading the virtualized app. You have a lot of data to proxify. I mean, like really a lot. If you want to hide your footprint, you have to hide the proxify definition, the proxify light definition. Like you have to hide and play a lot with that. And sometimes even the virtualization data are leaked. For example, that matching is not always 100% well done on the Proxify libraries, and you will have requests that are redirected to the system without being reproxified, and here start to be visible to the Proxified app, so we can detect, which is not good. So quite a lot to do. How to avoid detection method at system level? Because I've mentioned before at the application level. So at system level, I mean, we can start to first we have to make virtualization obvious. You're a privacy app. You're, I don't know, a multi-instantiation app. So it's justified. You're not hiding the justification of virtualization. And then you are user-specific. By being user-specific is very good because you can minimize the number of processed activity on your definition. You can minimize the number of permissions that you request. So like you're very hard to be detected as a footprint, for example, on the manifest definition. Okay, shall we be worried? I took like a sample of 15K application on 8 stores and tried to count what we have. We see that we already have quite, I say here, 0.2% of the application on the market that start to be very surprising. I mean, like, who ask 91 permission? I mean, like, why do you need 91 permission as a normal execution? I mean, like, there is one that is very funny. Like, it has 437 permission. Well, I mean, don't install this app. And then you start to see how many activities does this app pretend to have. I mean, like one app, very funny here again, like 1,216 activities. I mean, like for a very small app, that's kind of start to be very suspicious, okay? And here again, you see what? More than 5%, like if you combine together, 3% of the application available on the market have more than 120 process activity. I mean, like that should start to ring a bell. Like, why do you need 120 proxified activities? I mean, one need maybe it's like it's an antivirus that process the analysis of the other application. Yeah, I think that this antivirus has 140 process activity. But apart from that, why would you need that many process? I mean, like separated process activities. Like normally, it's not used. Like I didn't mention, but like I think that 95% of the application do not have process activity. Well, I've just mentioned here the one that have process activity. Okay, conclusion. Patching is complex. Yeah, it's interesting but complex. You have to see which method you can hook, how you can hook them, why you cannot hook other methods. I mean, I didn't mention, for example, why you cannot hook from the DEX of the Proxify app. You have the issue with what we call the JIT execution, the ahead of time execution for these subloading applications. You cannot. But we're still working on that. Proxifying opens up new opportunities, really a lot of new opportunities. And a lot, as I said, a lot of potential works exist. How we can stabilize the hooking framework to event crashing, to support new methods very well. How can stabilize detection avoidance framework to be like minimize really like nearly to zero the virtualization footprint. I mean, like nobody else does that. You just have to look how many process activity you have. If you grab under the APK libdex, I mean, you will find them that they don't even hide the name. But if you hide that, well, you will start to have a very good solution. As I mentioned, so this work was, as I said, was made through Protektoid. We're always open to new survey ideas. So we're working on proxifying and patching on the community side. If you have any other idea for Android, we're always welcome to work on new ideas. Okay, so thank you.